Okay, so our next speaker will be Jesus Fernandez Sanchez, and he will tell us about performance of new invariant methods for phylogenetic reconstruction. Thanks very much.
Well, thank you. First of all, I would like to thank the organizers of this conference for giving me the possibility of explaining these results, which are part of my joint work with Marta Casanellas. The aim of this talk is to present the performance results relative to a phylogenetic reconstruction method based on invariance. So the first thing to do is to explain what are going to be our hypotheses. Our starting point is an alignment of several sequences of nucleotides, and we assume that all the sites in the alignment evolve equally and independently under a discrete Markov process. We are going to consider phylogenetic trivalent trees, and for each branch of the tree, we consider a transition matrix, which is nothing but a Markov matrix whose entries are the probabilities of nucleotide substitution. Since these entries are unknown, they are considered to be the parameters of the model. And in this case, we say that the model, the evolutionary model, is algebraic. As an example, we have the algebraic Kimura 3-parameter model, which is a generalization of the Hughes-Cantor model and the Kimura 2-parameter model, and which is characterized by the fact that the entries in the transition matrix this one satisfy some symmetries. Well, given an alignment, a model, an invariant is just a relation being satisfied by the joint probability distributions. If the model is algebraic, this relation is given by a polynomial. We say that an invariant is a phylogenetic invariant if it allows to distinguish between different topologies. Phylogenetic invariants were introduced by Cavender and Felsenstein and independently by Lake in 1987. And since the introduction, they have originated a lot of works in mathematics. Let me recall the results of Evans and Speed, Steele, Allman and Rhodes, Stonefels and Sullivan, Hagedorn, and also in phylogenetics, Sankoff and Blanchett, Navidi, Churchill, von Hasseler, Allman and Rhodes too. And let me recall that recently there has been a lot of work in order to design and develop phylogenetic reconstruction methods by using phylogenetic invariants. For example, the work by Erickson and Yao for the general Markov model by using techniques from machine learning, or the method introduced by Casanellas, Garcia, and Sullivan for the Kimura 3-parameter model. Now I would like to recall briefly the idea behind this last method. Well, we focus here in the case of quartet trees evolving under the Kimura 3-parameter model. So there are only three different tree topologies. Our starting point then is an alignment of four sequences, and by counting the different columns in the alignment, we are going to obtain a point in some space, this point P. The coordinates of this point are just the relative frequencies of the different columns appearing in the alignment. Then the point is how we decide which of these different topologies is the closest to our point. The idea behind this method is to take the evaluation of a set of 8002 invariants on this point, then take the sum of the absolute values of these evaluations, and if we do so, we obtain a score for each tree. Then it's enough to choose the tree topology which minimizes this score. Recently, Casanellas and myself, we have improved this method by using techniques coming from algebraic geometry. And now, instead of using 8002 invariants, we have seen that it's enough to use 36. Now, in order to test the performance and the efficiency of this method, we are going to take Hilsenbeck's approach in his paper in 1985. To this aim, we are going to consider a couple of parameters, say A and B, which vary from 0.01 to 0.75 in increments of 0.02. Parameter A gives the length of the internal branch of the quartet tree and of two opposite peripheral branches. And parameter B gives the length of the two remaining branches. This way, we obtain a parameter space that we call the Hilsenbeck tree space. Now, these graphics here represent the probability of reconstructing the correct tree in the Hilsenbeck tree space for the methods of neighbor joining, maximum likelihood, and the invariant method I've just explained. Black areas represent regions where the correct tree is always estimated, and white areas represent regions where the correct tree is never estimated. Gray tones represent zones of intermediate probability. The 95% isocline is drawn in white, and the 33% isocline is drawn in black. Well, as you can see, the invariant method seems to be efficient, competitive for alignments of length bigger than 1,000. And neighbor joining and maximum likelihood seem to be more efficient. So why considering invariance if the already existing methods seem to be more efficient than the invariance method? Well, we have also tested our invariant method on non-homogeneous sets of data. Let me recall that in nature, there is wide evidence that evolution not always happens at the same rate. However, common reconstruction methods assume that all the transition matrices have this form, are the exponential of the rate matrix multiplied by the time, and this Q is the same rate matrix for all the branches in the tree. In this case, we say that the model is homogeneous. Since invariants are based on algebraic evolutionary models, and the parameters of these models are the entries of the transition matrices, it's reasonable to hope that phylogenetic reconstruction methods based on invariants are going to be highly efficient, especially for non-homogeneous sets of data. Well, here we have the graphics representing the probability of reconstructing the correct tree for non-homogeneous alignments of length 100. As you can see, the results obtained by maximum likelihood here in the center are not good, while neighbor joining and the invariance method have 99% accuracy. Let me say that for this simulation, we have used a standard version of maximum likelihood. In the graphic on the top, we have the comparison of the invariant method with two versions of maximum likelihood, the standard one and the non-homogeneous one developed in the package panel. For this simulation, we simulate alignments evolving under this tree where Q1 to Q5 are different rate matrices depending on a parameter epsilon. For epsilon equal to 1, the model is homogeneous, and notice that as epsilon increases, the efficiency of the standard version of maximum likelihood drops. We have also compared our method with neighbor joining for short alignments, and notice that for sequences of length smaller than 400, the invariant method outperforms neighbor joining. For longer alignments, the efficiency of the two methods are similar. And finally, to close, let me say two major motivations for using phylogenetic invariance. The first one, I've already said, is the fact that since phylogenetic reconstruction methods are based on algebraic evolutionary models, it's reasonable to hope that they are going to be highly efficient for the case of non-homogeneous sets of data. The second one is because is that the already existing methods, neighbor joining or maximum likelihood, are unfeasible for trees with a big number of leaves because of the computational time. On the other hand, the computation of the phylogenetic invariants must be done once and for all, and this computation does not depend on the length of the alignments. So this is all what I want to say, so thank you very much.
Any questions?
I mean, if you want to find out the reliability of such methods, any method that computes quartic trees, of course, you take just a few more sequences, 10, 5, 12, whatsoever, and you look at all the quartets. And there are simple criteria which tell you whether the quartet trees you get for each 4 of those are compatible, that fit into a tree or not. And so a simple test, sort of how well, at least the internal consistency of your method, would be just to check all the quartet trees you get with this method, and then see whether it satisfies this compatibility condition or not. In addition, that would have the advantage that if they don't fit into a tree, you can still construct something else instead, networks or whatever, and you could look at the 2 best quartets and try to get an even more adequate network. Did you ever try to sort of look at your result in this way?
No.
So I would suggest that you do some consistency tests based on investigating not 4, but 12.
Okay. Okay.
Any other questions? Okay, then I'd like to thank the speakers for the morning. So now we're going to have the group photo.